Right, guys. Today I would like to discuss with you, or say, look at the graph of a function and the graph of its inverse. There's a special relationship between the graphs which I want to highlight, and it's important that you know it and you can maybe use it wherever you need to use it. Now, what I'm going to do, let's take a simple function like, let's say, y equals to 2x plus 2. Right, I'm just taking a simple function so that I can easily illustrate what I want to illustrate, isn't it? Then you can take the whatever we discuss here to any other function and just make sure that you apply the same principles and move on. Is that right? Right. Now, first of all, let's work out the inverse of this function quickly. Now, to get an inverse of a function like this, remember, we said when you are working with an inverse, now your domain becomes your range and you work it backwards, isn't it? So what happens actually, I can illustrate this thing by saying the input, which is our x, which was from the domain, becomes output, isn't it? And at the same time, they say the output becomes input. Right. Now I want to see, how do I use this? How do I use this? I use this way. I will rewrite this expression exactly swapping around the x and y. So I'm going to have the x here, all together, and then say equals to 2y plus 2. This trick, or I don't know what you want to call it, but maybe not everybody can say, it will say this thing exactly the same way I'm saying it, but I'm saying things the way I best see them, and I best think I can put across my point and be understood altogether. So it's not standard that you will see any other teacher doing or lecturer doing the same thing altogether. Every lecturer or every teacher has his or her own booklet. Okay, so my booklet has got this thing. All right. So now what do we do now? Because of the reason that we plot functions on graphs which on the system of x, y coordinates. So once we've got this function here, it's not actually in the standard way we put function. So we must have our y as the subject of the formula. So where does that take us to? This does take us to saying x minus 2 equals to 2y plus 2 minus 2. Altogether, I'm trying to avoid that language of things moving around. I do a transformation on both sides of the equation, isn't it? Okay, a convenient transformation, because I know where I want to go. Is that right? So this will give us 0. 0 added to 2y is going to be 2y. And then we've got that. Then which means in the next stage, next step, you can put 2y equals to x minus 2. Then now to come back to y, we'll need to divide both sides by 2. Then we get y is equals to x over 2 minus 1. Okay, so then we can say this is f of x inverse. Remember, I warned you about this power minus 1. It's not real power minus 1. It's a notation which tells us we're dealing with a second function, the inverse, altogether. So we've got now here, let me just get this, erase this y here, and say this is our f of x. Still, you know, it's y equal to f of x, isn't it? Then on the other hand, we've got f second function. Actually, the best way to read this thing, you must say f second function altogether. Yeah. Instead, or say inverse of f. If you don't also say inverse of f, you can say f second function. Then x over 2 minus 1. Are we together, guys? Okay. So now, I think now we've got, since we're discussing the relationship of the graphs, these two graphs of these functions, I think now we must try to attempt to sketch the graph. It will be a rough sketch, but I want you also to go and get a graph paper somewhere, or then draw it nicely, and then you have a good feel of what we're saying is right, isn't it? So this stuff here, I normally don't like to use the word stuff, because when people talk about stuffs, they're talking about illegal things. So that part of work now, we don't need it. Let's just get rid of it to open a space for our graph. Yes? Maybe let's wait until we get to the graphs, then maybe an answer, partial answer to your question might come up. That's right. Just hold on. If it was a call, we'll say hold on. So now let's put our sorry. Okay. Roughly that's that. The system of axes. Now let's discuss this function first of all. The gradient is 2, isn't it? It cuts at 2, isn't it? Which means if we've got 1 here and a 2 there, 2, remember, I hope you remember this thing. A gradient is y2, y1 over x2, x1. So you run this distance horizontally and rise up or go down this distance. So it's going to be 2, which means it's going to run 1 above 1 here and go 3, 4, and then somewhere there we've got the point on the line, is it? Is that right? Okay. Then we can, I hope, let's pray that my line comes out nicely. I think more or less, isn't it? Okay. Then we've got that line. Did you see how I used my gradient to plot my line? My gradient is 2. Then I space it as a rational number, I say 2 over 1, isn't it? Then this 1 corresponds to the run horizontally, which this is the one I'm calling here. Then the 2 goes to the run vertically. If it was negative, it would go down, but it was positive, it's going down, up, isn't it? Then I've got a point on the line there, I've got a point on the line there. All together. So now, let's come to the second line. The second line is 1 over 2, which means following the same system, let me put it in color, in brackets there. Then this would look like 1 over 2. All together. Now what's going to happen? I'm going to run 2. First of all, I have to tell me where does it cut? It cuts at 1, isn't it? It cuts at 1. At minus 1. So, minus 1, sorry. So we'll get minus 1 there. Let me take black ink. Minus 1 there. Minus 2 there. Then 2 there. And I don't know where to put that in your check there. So what happens now? It runs 2 horizontal, isn't it? That's right. From minus 1. It runs 2 horizontally. Then what does it do? Does it go up or down? Up, how many? 1. So, if it goes up 1, it will cut there. You agree? Yes or no? Do you agree, guys? Yes. Okay. So now, then the line roughly will come more or less like that. Let me say undo, undo. Then say, yeah. Now I wasn't breathing now. Before I was breathing, so I couldn't do it. Some of these things, when you do, they must hold your breath. What is it, my sister? I can see you are questioning something. Right? Yeah. No. Let's just start afresh again. This thing says run this distance horizontally and either rise or go down this distance. But rising or going down depends on the sign of this number. So what is happening here with 2 over 1, which is 2. So we ran 1 horizontally up to above 1 here. Then from there, 2 is positive. We went up 1, 2 steps. Are we together? That's very important to know how to do. Are we together? Okay. Then on the other side now, the other only for the other line now, the gradient is half in brackets. There is the right one. Is it? So what happens now? We have to run 2 horizontally. We run from where? From where the line casts. Actually, not from where the line casts. From any point of which we know is on the line. Is it? Now we know that minus 1 here, 0 minus 1 0 is 0 minus 1 is the point on the line. So we go there. Then we run 2, 1, 2. Then once we run 2, then we rise 1 because 1 is positive. We go 1, we're there. Then we're done. Yes? The reason why they intersect is because they are not parallel. That's the simplest reason. But I think part of your question is actually what I'm trying to answer with this question, with this lecture. So can you hold on again? Okay, thank you. I'm not saying it's wrong. It's right to, as you go, ask questions. Isn't it? Ask questions. Then that is the thing which is going to generate some kind of learning. If you have got a question, ask it. Then I'm answering you bit by bit. But when I get to a point where you full question answer, we're going to wrap up and say, see what you're asking, this and that. Is it? Okay. Right, so that's the story now. The question is, why is that linear inverse cut at the same point? I'm saying that is part of what we're doing today, isn't it? Now, remember, from what we know, what's from yesterday, we know exactly that if we compose f with its second function, by second function, and I think now we all know, we mean the inverse, isn't it? With this second function, we must get the identity function. The identity function is that function which takes x to x. In other words, it says y is equals to x. Let's plot that function. Let's plot that function, isn't it? Where is that function? The function is the bisector of the first and the third quadrant. So it will come, maybe let me take a color for it, because it's a special line. It will then come this way. Oh, roughly like that. All together. So that is the line y is equals to x. y is equals to x. Good. Now, I think I'm about to answer your question now. Always take that thing as, I don't know, maybe it's God given. It's God given. Always, when you're dealing with a function and its inverse, you graph them. The graphs of the two functions, remember that there are two functions, a function and another function, its inverse, isn't it? So the graph of the two functions, they are always going to make a symmetrical body. The line of symmetry is going to be the graph of the identity function y is equal to x. So in other words, if I part here, let's look at the one thing which is very obvious. From 2 straight to 2, I think it looks almost obvious that this distance and that distance, they are equal. Is it? Now do you see that the point of this line here is on the mirror line, and the point of this line there is on the mirror line. Where is the mirror line? The mirror line is exactly on the mirror, so the image of that point is exactly there. Then I think you can see now why they should come together, because these graphs, they are going to be symmetric around y is equal to x. Is that clear? Okay, I hope that is very clear. So what you can do now, you can go and take one or two functions, do exactly the same thing, try to graph them, and later I'm going to teach you how to do graphs on the computer, which is going to be faster. Then you can easily get the graphs very quick without putting a lot of numerical calculations altogether. So guys, at this moment, we have looked at the graph of a function and the graph of its inverse. We've discussed how to get the inverse from a given function, that thing of swapping around the x and y, and manipulating, making y such as a formula. Then we've come up to plotting the graphs roughly, but I think we can get the idea that those graphs, they will be symmetric around the y is equal to x. How can you apply this? Maybe I want to give you an exercise. Use this kind of knowledge. Let me maybe create a space for an example. I'm just trying to say, how can you illustrate, use this, or how can I check that you understand what I mean? Let's look at this example. Let's say I give you a graph of a function, and this graph for a function is something like this. And I say this is f of x, I would say y is equal to f of x. Then I say, immediately say, please insert the graph of the inverse. Who can tell me what are you going to do? What do you think is the first step we're going to do? You don't know the function. I don't have the expression of the function. I don't have something like x squared plus 2x, whatever. I just have that graph. And the order is that please insert on this system of coordinates the graph of the inverse of this function. Yes, my brother. This guy says, I will put the graph bisector of the first quadrant and the third quadrant. Yes, I think that's a very important step, isn't it? Yeah. Then what are we going to do next? Yes, another person? We haven't talked about y is equal to minus x. We said these graphs are going to be symmetric around y is equal to x. Try something similar. Try something similar. Then let's discuss it.
No, I think the reason why we are using this graph is because of
which A?
The coefficient of
No. I don't think that is got any influence. This thing is standard, my friend. If you have got a function and a graph, a graph of function and its index. The graphs are always going to be symmetric around y is equal to x.
For example,
that's what I'm saying. Let's not debate a lot. We're going to miss something. What I'm saying, take an example of your own, like the way you are thinking. Work it out fully, then let's come and discuss it. Yeah, that's the challenge I want to give you. So now, how do you proceed? Somebody who can suggest how would you proceed now from there? From this graph, now you want to get the graph of the inverse. How do you then proceed? You know what I'm going to use? If you did physics or science, I don't know what type of science you're doing at the moment at school, but when I was at school myself, we used to do some elementary physics, and one of the experiments was to test what is the distance of the image from the mirror as compared to the distance of the object from the mirror. Then there's an experiment you do there until you establish that the distance of the image from the mirror is equal to the distance of the object from the mirror. So we use that kind of fact. How are we going to use it here? Okay, tell me what you're going to use. Yeah, but what I'm telling you about the image of mirror is very quick. Let me just show you what I'm going to do. Let me just show you in one example. Ne? This line passes through the origin, isn't it? I can just draw a vertical around it. Take that distance, transport it vertically across. Once I take that distance, transport it vertically across here, I've got a point on the inverse. Do you agree? Then I'll do that with many functions. This point is also on the inverse. Why? Because it's on the mirror, the distance from the image from the object is 0, the image is 0. This point is on the inverse. All together. The rest will follow. So what I'm going to do now, I'm going to try to get this shape on the other side roughly, coming through here. Then get this shape coming through here. Then get this shape coming through there. Then get this thing this way. I'm done. Do you believe me? Are you convinced? You must be convinced. You really, if you're not convinced, argue. But try to try to negotiate with yourself in a way that this thing makes sense. That is what I'm doing there. That's the reflection. Is it the mirror is reflect the object on the other side? Reflection. What do you mean by reflection? You mean if you reflect something, this mirror is here, the object is here. If you reflect this object that side. That's what I did with that with this thing, this kind of discussion here. This is what I did here. I'm reflecting this point to this side. I'm reflecting this point to that side, but that point is on the mirror, so it's reflected on the mirror itself. I'm coming here, reflecting that point to the other side, but it's on the mirror, it's reflected there. Then now what do I do? I'm trying to reflect all these points on the other side by trying to play around with this shape. That's actual reflection. Good that you reflect it up is actual reflection. You might maybe do it different the way you approach it, but in essence it's the same thing. Yes? Swap the coordinates. This is the other thing. If I've got a system of x's there, and it's on the Cartesian coordinates, which are marked very well, I can see the points, the coordinates. You swap around the coordinates. That's another idea. I never thought about that. Good that you brought it up. All together. Yeah. So this is what I'm saying, that as you engage and talking, I'm talking things from my point of view when I say, you see the other point, also bring it up, negotiate it, we broaden what we're understanding. All together. Good. Is it beautiful? It looks beautiful to me. If it doesn't look beautiful, it's not because it's not beautiful, it's because your eyes maybe might have a problem. Good. Thank you for that. I think I'm going to stop there and then pass over to something else. But before that, I hope I emphasized before that once you've got this kind of a situation where you are composing a function and its inverse, I hope I mentioned this before, you get x. I said this is actually the machine for solving all equations. Did I say that? Did I tell you that this is actually what makes equations possible to solve? Did I tell you? Okay, so that is fine. So thank you for listening there. Let's